Well, thank you everybody for being prompt, coming back. Just in case there were a lot of new names this morning, my name's David Ross. I look after technology for Innospec Performance Chemicals in Europe. I have the pleasure of doing this presentation, which has been put together by Nabuzwe, who couldn't be here today. And what I'm just going to be doing is going through and presenting the information that's there. Hopefully you'll actually find this interesting, slightly different to the presentation that you actually had this morning. First thing, the agenda that we're actually going to do, I wasn't quite sure if everybody actually knew our company, so I've just got a couple of slides on the company itself, just so that you're aware of who we actually are. Then I want to look at briefly at the key emissions, the key metals for low carbon emission, and look at some industrial initiatives that are actually in place, so sort of setting the scene. And then going through different parts of the process, which I know quite a lot of you are already familiar with. And what I want to try and do there is bring out examples of where potentially we could actually try and improve the environmental footprint there. And then just a conclusion. I'm Scottish. I speak quickly. If you can't understand what I'm saying, it's not clear, stop and ask me, please. If I start to murmur, it's because I've got lost in my notes. Okay. So the first thing, introduction to Innospec itself. We are actually a company, the name itself is quite interesting. Innospec was really only formed in about, I think it was 2006. And that's when we actually reinvented the company, because the company was originally associated octel. Its principal product, tetraethyl lead. Everybody stands back in aghast at a conference to do with environmental concern when talking about tetraethyl lead. The company had to reinvent itself. And so they actually did that. The name Innospec, Innovation Specialities. That's where the actual name came from. The company itself is over a $1 billion company. It's made up of 3 different divisions: performance chemicals, fuel specialties, and oil field. Both Charlotte and myself work in the performance chemicals division of the company. The R&D that we actually have, if you look at, we've got a turnover of about 1.3 billion. Our R&D on a global basis is about 30 million. So it shows you that we are quite committed to that innovation approach on that. The mineral extraction part, we renamed it. Originally we called it mining, but the mineral extraction part actually came from the acquisition of Huntsman by Innospec. And we renamed it to metal extraction because our fuel specialties actually sell into the mining industry, but they sell the additives that are used in the machines that are on the coal face. So two totally different industries, and people were getting confused about that. What I'm really looking at is what our capabilities actually are. So the products for mineral processing, we're really looking at froth flotation and hydrometallurgy are the 2 things that we're working with. Research, development and manufacture. We have research labs to do with mining are in the United Kingdom and South Africa. Our manufacturing footprint is Europe and the US. We do have labs in Europe, Central Europe as well, but they're not connected with the mining industry. We are a global supplier. And we have a very strong network, but prominently based in the European forecourt. I want to look at now the actual areas that we are focused in. So looking at the actual metal extraction. Our real operation, if you like, is in the froth flotation and hydrometallurgy. What we really focus on is working with customers. Where we're good is trying to solve problems. And that's what we're really trying to do as an objective. We have to target in certain areas. We can't be everything to everybody. Hence the concentration on flotation and hydrometallurgy. Where do we differ from some of the other suppliers? the thing that we really sort of pride ourselves on is we're combining the idea or the knowledge that you actually have with metallurgy, combining that with colloidal science, and combining that with surfactant knowledge. And putting the three together, we're trying to there use those other theoretical approaches to actually solve the problems that you actually have in mining, in mineral extraction, sorry. Sustainability is something that's very, very key to Innospec, and we have actually been working on this since 1999. It's been a focus for us, and we published our first sustainability report in 2020. And that sustainability, the new sustainability report for 2021 will be out in the next few weeks. I haven't brought sustainability reports with me. You can actually see these on the web, and when it's published, it seems a bit of a contradiction in terms to be talking about environmental and then bringing printed documents to you on that. I want to now sort of set the scene in terms of what we want to try and achieve. And this is rather topical because it was a conversation around the lunch table. Metal prices. We've seen a big difference in metal prices going on in the way that the metal prices have actually changed. So you've seen a decrease in, if you like, the importance of the precious metals, and then an increase in the value of the metals that are being used in the electrochemical area, particularly in the batteries. If people have actually tried to buy a car over the last few years, you'll know how difficult it actually has been, because certainly in Central Europe and the UK, the waiting time for a standard car these days is anywhere between sort of 12 to 18 months, sometimes even 2 years. And the reason for that is they can't get the parts that are required either for batteries or for printed circuits. And that's where we're really falling down. You're getting companies like Mercedes and General Motor actually selling cars that haven't got the full spec on because they can't get enough chips to actually put into the car, which is an interesting way to actually look at it. One of the things I think that's going to be covered in the next presentation is what are the risks, or what actually happens. We came across this chart which actually shows the areas that have been important in terms of the mining industry and metals. And you can see it in 2021 that you had ESG, and ESG has actually grown a little bit in 2022. And obviously here, what you actually had was of great concern last year about COVID, and that's really dropped off the radar now. But what is still on the radar are the consequences of COVID. So things like resource nationalisation. People can't get enough resource. Supply chain. You can't get supply chain. It's very, very difficult. It can be unreliable. The other thing that you're actually seeing is a very strong change in the way that companies are actually looking at climate change regulation, which is what we talked about this morning. And this has really been forced on the mining industry because companies, banks and insurance companies do not want to invest in things that are being detrimental to the environment. The other thing that you're actually looking at, and everybody's talking about, is the energy costs. People are literally struggling on those energy costs. Now, I'm sure there's probably other ways that you can actually look at this, but we were just trying to look at what the changes were between last year and this year. I don't think there's any real surprises there. I want to look at the key metals that you actually have, and just a few words on each of these. So the main metals that you're looking at in the electrochemical side are obviously copper, cobalt, lithium, some of the rare earths and nickel. And we actually are seeing movements away from some of the more traditional metals into new metals, which is causing a challenge to this industry in particular. I'll just look at 4 of these in a little bit more detail. And no surprise that you can actually have is that in the copper market, you've got this gap going forward. And this is all down to the fact of the demand for batteries, for electrical, that you're actually seeing there's a growing gap that's actually in there. And it's the same for cobalt, that you're actually seeing that the demand, there's a deficit, quite a large deficit going forward into 2030. And how we can actually overcome those deficits are important. What I want to look at here is you've got lithium, where we've got untapped resources at the moment, which we want to actually explore. The problem with lithium, as you all know, it's not exactly the easiest metal to actually refine. So that gives you a different challenge. And then you've got nickel, and people want to move towards nickel. What makes this a lot more complicated, as you all know, one of the biggest areas that you actually get copper from is the DRC. And you're also seeing that a number of companies, for instance, Tesla, are saying they do not want to source from there because of the ESG issues. And people are beginning to move away from them. That's given additional challenges because it's putting the squeeze on these market shortfalls even further. All right. And just how is industry trying to actually address this? Again, this was a topic that we actually had over the dinner table, the lunch table. What we're actually seeing now is that mines that were not workable are now becoming workable because the cost that you can actually sell metals at means that these are more attractive. So you're actually seeing things like, for example, you're actually seeing Clelco have opened up a mine that they actually closed because it wasn't profitable. And we're seeing big investments in new mines, which the grade of copper was a lot lower than it used to be. Now the difficulties in actually mining that are such that the cost, it makes it worthwhile actually starting to put that investment in. So we're seeing big investments actually occurring. I want to now really concentrate on copper. So I've tried to set the scene there. We've got a shortage in metals in the targeted industry that's going. How do we actually resolve that? And I want to try and use copper processing to try and demonstrate some of the ways that potentially could help with that. I want to look at the different things that you're actually looking at, moving from, as we all know, phase one, where you're talking about taking something that's being crushed and then concentrating it through the flotation process and the thickening process. And then looking at the phase two, where you then extract that and purify it. And depending on whether you go through pyrometallurgy or hydrometallurgy. When you actually get to these, you're taking something that's an ore that might be 1 to 5% copper, and then you're taking it to a plate of the electrowinning cell or the electrochemical cell, electrolysis cell, that's going to be 99.99%. Now, the assumption there is that, well, that's really good because you get 99.99%. But the problem is you get 99.99% on the electrode, but you've actually got probably somewhere between 5 and 10% of copper that's gone into the tailings. How do we actually get that out? That's a big number. So how do we actually improve that process? So really want to look at now, when you're looking at the flotation area, and trying to see what we've got. Now, obviously, you're all in this industry, you know what the flotation is about, and from your flotation, you're then looking at getting the material into the flotation. You're looking at getting the mineral and then floating that off. You're then taking that float and you're concentrating that. And you're concentrating that normally going through different processes, which normally require the product to be solubilized and then concentrated further. So there's about 3 different types of process. One of the traditional ones is the pressure process, where you're actually taking this, you're taking the thing from the flotation through the thickener cell and then into the pressure oxidation, where you're then getting the copper out as a solution, which then goes through and into the solvent extraction and through the electrowinning process. in both of these, you've actually got tailing processes that come out on two different parts of the process. One of the areas, this obviously is a capital intensive piece of equipment, and you can obviously do this in a bulk tank as well, where you've got the settling in there and doing it at atmospheric pressure. One of the newer areas that you've actually got is copper processing using bacterial leaching. So bioleaching that's actually there. And this is where you're actually using quite an intelligent way. You're using little bugs to go in there, and they're actually attacking the ferrous sulfate, sorry, and they're actually converting that ferrous sulfate into ferric oxide, and getting the H2 and getting the sulfuric acid produced. The ferric oxide is a very strong reducing agent, as you know, which then actually oxidizes the copper, and the sulfuric acid then dissolves the copper and then takes you into the electrowinning process, the solvent extraction and the electrowinning process. And it's very interesting to see that very recently there have been a number of papers that have been using specific bacteria to actually leach copper out of circuits, which has been one of the biggest challenges that we've actually got in the industry, because recycling precious metals that are used in the electrical industry has been more expensive than actually getting virgin material. And now we're actually seeing that there are processes coming that are available that are going to actually rework this. Now, in the terminology that we normally use, that would be referred to as grey material as opposed to virgin. And that might be one way to actually propose sort of closing this gap that we actually have. One of the other processes obviously is a heap leaching, where you actually take low-grade material and in essence you just spray sulfuric acid over that. When you're actually doing that, you're obviously dissolving the copper, and then you're collecting that in a pool, and then you're concentrating that through the normal cycles that you're actually looking at. And once you actually go through that, the next stage that you're actually looking at is the solvent extraction. And in the solvent extraction process that we're actually going, you're looking to get as high a concentration of the pregnant leach, the pregnant leach solution in that first separation, and then going into the second solvent extraction process, where in essence you are actually then flipping the solubility between the solvent and the aqueous layer, and then changing that back to go into the electrowinning process. And anything that interferes with that is going to actually then reduce the efficiencies of your process, and that can actually happen. So in the processing, what have we actually got as issues in this processing? You've got crud formation, you've got entrainment losses, you've got the poor phase disentanglement or disengagement, the transfer kinetics when you're looking at the solvent and water system, and then you've got losses of solvents, you've got continuity flipping, and then if you go into the electrowinning process, you've got the formation of acid drops, which is a major concern. So I just want to move a little bit through these, taking the first one where you're looking at the crud formation. And really this is where having particulates in there is not helping you, because you form an emulsion between the aqueous and non-aqueous phase, the organic phase, and that emulsion gives you this crud. And in essence, the particulate matter in there stabilizes the emulsion, which you get here. That stabilization is referred to as a Pickering emulsion. It's very difficult to actually break that down. The bigger that phase there, that crud phase, the bigger that is, the more copper you're actually using, and then has to go back through the recycling then again. And you can see, sorry, that's not come out very well. You can see what that crud looks like on this photograph. Hopefully when you actually get the presentation, you'll be able to see that a little bit better. Sorry. Then in the second part is you're actually looking at electrowinning, and you get this acid mist formation. And the acid mist is actually where you've actually got small bubbles that are coming off the electrodes, that are bursting when they actually hit the surface. And when they burst and they hit the surface, they're actually taking the sulfuric acid into the air. And that's causing both worker problems and also problems in the plant where you're getting corrosion of the equipment. And so what we're actually wanting to look at now is what influences these. And by looking at what influences these, we can look at how we can actually improve the process. So the first thing that I want to look at is colloidal silica. Now, colloidal silica is one of these things that, as you know, you get it in all the different ores. Sometimes it's only there at a very low level, which doesn't interfere with the process. And other things, it actually is there at quite a high level, and it can actually interfere strongly with your purification process. So you have two types of silica particles. Ones that are partially leached, so they're quite small, colloidal, and they can have both positive and negative charges. Normally, the ones that are hydrophilic, are totally dissolved, and they're not a problem for you. You're looking at the ones that are hydrophilic in nature that don't dissolve, and they can actually come out. So you get the salicylic acid, formed in solution. That then dissociates, and it then from dissociation can then polymerize. And when you actually get that, you get the particle growing. And that particle then grows out of solution and forms the colloidal silica. The colloidal silica is such a small particle that you can't actually pull the particle together. And so it's very difficult to actually remove. And that's one of the problems that we actually have in the industry. And that has really serious implications, as it says on the slide, in both the solvent extraction and the ion exchange process. So where are these actually coming from? You're going to see three slides, and the three slides are going to be very similar. And the difference to show you, in this left-hand side of the slide, you're actually seeing where the silicon comes in. And it's the leaching process where it gets dissolved as you're actually trying to dissolve the targeted metal. And you've got the leach tanks, the autoclaves, the heap leach, which I've talked about, those three. I didn't talk about in situ leaching, but in situ leaching is coming more and more relevant when you're looking at things like lithium metals. And so you've got all of these that are actually, when you've got a high silica content, they're getting dissolved in there. You then go through your purification process, through the center part of the process, which is here, and you're looking at actually trying to precipitate this and filter it and clarify this. If you're not successful in actually doing that, what happens is that then passes through and you have the silica problem coming through into your solvent extraction process. And that's the last thing that you actually want. Because if it's not treated, you're going to actually then influence the performance. So why is the colloidal silica so difficult? First thing, it won't filter. It's too small. It goes through the filter. The second thing that's actually is important about it is its size is such, even though it's only there at a very small percentage, it actually is in a very large quantity. And if you think of like a bag of peas, frozen peas, and you think of all of them stacked together, you've got these small colloidal particles stacked together. So that means that the silica particles that are there can't separate, they can't settle to the bottom, so they're sort of suspended. That's one thing that's really important to try and control. Because if you can't get that settling out, that's then having to be removed by filtration. So it doesn't affect, it impacts the efficacy of your process. The other thing so what you actually need to do here is you need to actually increase the size of the silica particle, the colloidal silica. And by increasing that size, it moves from something that will not settle to something that will settle. So that then removes your process. So it's very, very important to actually do that. And we normally do that by a process called coagulation. And in doing your coagulation, what you're doing is removing that by increasing the particle size, and you can then do that. Then you would flocculate that particle, which is then very, very good to actually, very easy, sorry, to filter, and therefore removed out the process. How is that actually done? There are two different types of coagulants normally used. There's the one without charge, referred to a neutral product. And then there's the one with charge, which is normally a cationic product. And what you're actually looking at here is that the product itself competes with I'll go back one. The silica particle then associates with the water. The water then gives you a crystal, and it keeps the particle apart. What the actual coagulants do is they interfere with that water absorption and displace the water and stop the water going on, which then allows the silica particle to come together, and then the silica particle grows. And that is the mechanism by which we want to try and to actually promote to get this as effective as possible. Now, when you're actually looking at that, what you will see in two different parts of the process, if you are looking at the filtration area, you can see here on the as you're looking at it, the left-hand side of the cell, you can see no additive is actually in there, and you can see what it actually looks like. It's quite difficult to actually bring that. As you then increase the coagulant in, you can actually see you're getting a better separation, which means it's a lot easier to actually filter. It goes through your process a lot better. You get a purer product. The other thing that you're actually looking at is in the solvent extraction phase, you're looking at the separation that you get, or the disentanglement. So if you look at your interface between the water and the organic area, that is actually separating more effectively. And you can see here, you've got a nice, you can't see it very well, you've got a nice blue layer at the bottom, whereas it's continuous here. You don't see any actually difference. And that's very, very important. What's the difference between the two different types of coagulant? Well, when you're actually looking at a non-ionic coagulant, you can see here that the dosage response. So you're looking at how effective it is in terms of increasing the dosage and removal of the silica. And then you're looking at the cationic one, where you increase the concentration, and you can see you get to a certain point, and then it's actually detrimental. It actually promotes again the separation process, so keeps things in particles. What's actually happening here, if you're looking at this on a molecular level, when you actually get the non-ionic type, the non-ionic type actually displaces the water. If you remember, that then allows the silica particle to come together. When it actually has done that, the non-ionic then comes off the surface. And by doing that, it then goes and it can work on another one and keeps that, so that process keeps going, so it's live. So you actually get that, you don't get any interference, you get to an equilibrium. With the cationic, what happens is the cationic covers it so far, which is up to here, where you get the minima. But then if you keep on adding the cationic, what it's doing is it's actually staying on the surface of the silica particle. So instead of actually having that negative charge keeping the things apart, repelling, what you've got then is a positive charge which is keeping them apart. So you're actually seeing it's a different process that's actually forcing the silica particles apart, but it's actually detrimental to the process that you're actually wanting to do. So it's important when you're actually doing these to actually identify how you want to do it and optimize the actual dosage level, so that you actually are making sure that you're getting an optimum performance. Just to be absolutely clear, we make a product which is the Descovix XC12, and we did this sort of chart, and you can see how the colloidal silica, or the insoluble silica, decreases through the process. The soluble silica is not affected. It stays constant. But it's that insoluble silica that's the problem. That's what you really need to actually get out of your process on that. So I just want to I just want to just put one slide up just finally on the SC12. And the SC12 works very well in this area, and the important points about this is what I've tried to get through in the presentation. The point of addition is very important. It needs to actually go into the process prior to early on in the process, so that you're not actually interfering with anything else. So before you add any flocculant. If you don't do that, if you don't do the coagulation first, the flocculation won't work properly. The second thing that's extremely important is that you actually have to have good mixing there. And that good mixing is really important. And some people think that the mixing is something that is, it can be detrimental because it can actually break particle size down. If you've got your if you've got your coagulant in there, that's not a concern. It will keep going. It won't be detrimental to what you actually are doing. And then the other thing that's important is the benefits that you actually get, which are highlighted in the bottom of the orange box. So that's one thing that's really important to try and get that under control. Obviously, when you're looking at this, the silica contents vary. And if you've actually got silica actually in there, it's important to keep the silica treated all the way through, rather than try and continually changing your dosage. Because once you actually get it into your circuit, it's hard to get back out of your circuit. So you've got to make sure that you actually keep that treatment constant. I want to now move on to the electrowinning process and really about the acid mist. In here, you're actually looking, as I've mentioned before, you get the bubbles formed on the electrode, and those bubbles then come up and they actually burst on the surface. This can be treated in a number of different ways. There are physical ways and chemical ways. So the traditional way was to actually put plastic balls onto the surface, which you can see here, which try and actually just stop that mist breaking onto the surface. Something that is a more recent development is the use of hoods, which obviously mean that the acid mist is not being stopped, but what it's actually doing is stopping it, getting it into the atmosphere. It's staying in the cell itself. Obviously, the easiest way of doing this would be forced ventilation, but a lot of these plants are extremely large plants, and forced ventilation is something that would be very energy intensive. And then the last way is the chemical reagent. And the chemical reagent is what, obviously, as a chemical company, we are more interested in. And that's really when you're looking at putting that additive in there that actually stops or reduces the acid mist formation. Product that we actually have, you're looking at the reducing that airborne bit, and how you're doing that is slightly changing the viscosity at the interface of the bubble and changing the bubble size. And that is then giving you a way of actually reducing the bubbles reducing the mist that actually goes into the atmosphere. The second, what we've actually developed is, obviously there's one product already on the market here that does very well, or a number of products, and they're all based in fluorochemistry. And fluorochemistry is something that we want to get away from for various reasons. So what we've actually done is we've developed something that's non-fluorochemistry that actually works as an acid mist suppressant. And what we've actually found is it not only works as an acid mist suppressant, but it also helps actually smooth the surface of the electrode. So it's got a double benefit in the electrowinning process that is actually carried out. I just want to get on to the conclusion that I want to say. A number of points. I've tried to look at how improving that copper extraction process will actually work, and the benefits that you're actually looking at there are the efficiencies of the plant, reductions of your waste, and better, better conversion that you're actually got. So looking at the different points, at the moment, we're seeing our resources are being put under a lot of demand at the moment, and that things that we would not have processed before are now becoming processed. As a consequence of that, what you're actually looking at, you're trying to go towards zero carbon emissions. And everyone is trying to achieve these. The impurities that you actually have now are such that they are really more difficult to actually deal with. So you need to develop new processes, refine the processes so that you can actually handle these a lot better. You've got that increased use or increased demand for the metals that are used in low carbon emissions, which has led to the increase in production of other metals that weren't that well used before. And then what you're actually looking at is what I mentioned is you're getting the conversion of newly discovered lower grades of metal that are now actually being promoted, refined, because the demand is there and it can actually be paid for. I just have one more slide. I know normally in a slide you normally finish with your conclusion, but I just wanted to close with one additional slide on another bit that it might help with in getting an improved gold recovery. And there I want to talk about a product which is used for carbon blanking. And so, what you're actually trying to do here, as you're all aware, is actually remove the carbonaceous products that are in there that might compete for the gold complex with the cyanide. And what we've found with a product which is DG30, that we can actually find that we can actually get an improvement in terms of the amount of product you're getting and an increase in the recovery of the gold that you're actually getting out of that on your gold manufacture, That's really all I've got to say. I wanted to show this because it's different chemistry to the ones that we've actually talked about before. That is my last slide. I thank you for your attention. I hope you've, yes, that's my last slide. I hope you found that interesting. It's different to what we've had this morning, but what I want to try and see is the way that chemicals can be used to improve the efficiency and help that ESG. And the other thing that we're working on, the way that our chemicals are actually sourced and how we can get them with a better footprint, and that we can actually have them both on natural and petroleum based. A lot of people, we sell, most of our sales go into the home and personal care market. Natural is very, very strong there. Naturally doesn't necessarily mean it's best in terms of the ESG footprint. People make that assumption, it's not always right. But we're working on both areas there. I didn't want to go through our product list. Appended to this presentation is a summary of our products. There are some leaflets which unfortunately, due to the fact they weren't posted early enough, didn't get here, but I think Haarla are going to circulate them when they're actually there. When you actually go through our product list, if there's anything of interest, please contact us and we'll try and help. The important thing is to talk about it. That's all I've got to say. I hope you found that interesting. Any questions? Yeah.